Wulingyuan, Hunan Province. Towering sandstone pillars rise straight out of the jungle, disappearing into a blanket of mist that rarely lifts. It was this surreal landscape that inspired the floating mountains of Avatar, a place where nature seems to ignore the rules of gravity. It's also one of the last places on Earth where anyone would choose to build a bridge. There is no river to cross, no highway to connect. Just a 430-meter gap between two cliffs with 300 meters of empty air below. No construction platform, no solid ground, nothing but open space. And yet, engineers didn't just build a bridge across that void. They built one with a floor made almost entirely of glass. So how do you construct a bridge where even reaching the construction site is a challenge? And how do you make thousands of people trust a transparent floor suspended 300 meters above the canyon? Join Breakthrough Engineering as we uncover how China built one of the world's most extraordinary bridges, the Zhangjiajie Glass Bridge. Before a single cable could be stretched across the canyon, engineers first had to answer a much more important question. Could the mountain itself hold the bridge? Spanning 430 meters, roughly the length of 4 football fields, the bridge would transfer every load into the sandstone cliffs on either side. Wind, the weight of the structure, and up to 800 visitors at a time would all pull against the same anchor points. If the rock wasn't strong enough, nothing built above it would matter. Engineers carefully investigated both cliff edges before excavation began. Once suitable locations had been confirmed, foundation pits were cut into the rock, steel reinforcement cages lowered into place, and concrete poured in carefully controlled stages. Above ground, 4 towers slowly emerged. Their job? Guide the enormous tension from the suspension cables safely into the mountain. Behind the towers, the main cables disappear into 2 massive, invisible anchors. A tunnel anchor blasted into solid rock and a gravity anchor of thousands of tons of concrete, holding the full weight of the roughly 2,200-ton bridge through nothing but rock and mass. With 2 stable anchor points complete, only one problem remained. How do you connect 2 cliffs separated by 300 meters of empty air? The answer started with something almost insignificant, a thin pilot line. By itself, it carried almost no weight. It wasn't meant to. Its only purpose was to pull a stronger line across the canyon. That line pulled another, then another. Step by step, the system grew stronger until the first heavy steel cable could finally be drawn from one cliff to the other. For the first time in millions of years, the canyon was connected, not by a bridge, but by a single cable. Everything that followed depended on it. With the main cables finally suspended, workers began building a temporary catwalk directly beneath the future bridge. Steel cables and lightweight panels that became their workplace for months. Every inspection, every connection, every bolt happened hundreds of meters above the canyon floor. Strong winds could stop work without warning. The narrow catwalk would begin to sway, making precision impossible. Out here, nature decided when work could continue. Unlike open terrain, a narrow gorge acts like a giant funnel. Wind accelerates between the cliffs, changes direction unexpectedly, and creates forces that can't be predicted by experience alone. Before construction moved any further, engineers spent 6 months testing the bridge itself. Wind tunnel experiments, aeroelastic studies, pedestrian comfort simulations, vibration analyses. Every test answering the same question. Would the bridge hold steady no matter how violently the wind moved through it? Engineers exposed their models to wind speeds of up to 56 meters per second, around 201 kilometers per hour. The results forced a major design change. Architect Haim Dotan had imagined the bridge as an almost invisible ribbon floating between the cliffs, with completely transparent glass railings leaving nothing between visitors and the view. It was a beautiful concept, but it wouldn't survive the wind. Simulations showed the glass railings would act like giant sails, catching every gust instead of letting it pass. The idea was abandoned. Instead, engineers installed open steel posts, letting the wind pass straight through. With the foundations complete, the tower standing, and the main cables stretched across the canyon, the bridge could finally begin to take shape. The first components to appear beneath the main cables were the vertical hangers, steel cables installed at carefully calculated intervals to transfer the weight of the deck into the suspension system above. Then came the steel deck. Each section weighed several tons and had to be lifted slowly from the valley floor, guided carefully into position before being connected to the growing structure. Progress was slow by design. Even a small swing could prevent a segment from fitting perfectly once it reached the cables. Piece by piece, the bridge extended from both cliffs toward the center until only a single gap remained. High above the valley, crews lowered the final steel segment into place. It fit with millimeter precision. The steel spine of the bridge was complete. For most suspension bridges, steel is the story. For this one, it was only the beginning. The deck was designed with a gentle upward curve, allowing it to settle naturally once thousands of visitors began crossing it. Then came the feature that would make the bridge famous, its transparent floor. 99 walkable glass panels form the deck. Each measures 3 by 4 meters, about the size of a small bedroom, and is 50 millimeters thick, made of 3 layers of toughened glass bonded together with 2 SGP interlayers, manufactured from low-iron ultra-clear glass for maximum transparency. Every panel was inspected before installation. A single defect was enough for it to be rejected. Heavy suction lifting systems lowered each panel into place millimeter by millimeter before it was set onto rubber bearings, secured, aligned, and inspected once again. Expansion joints allow the glass to expand and contract with changing temperatures, while vibration dampers prevent thousands of footsteps from building into larger movements across the bridge. But calculations weren't enough. The glass had to prove itself. A single panel held a 40-ton truck, roughly the weight of 6 African elephants, and deflected only 2.16 centimeters. Then came the demonstration that captured worldwide attention. Workers struck another panel with sledgehammers for 5 straight minutes. The outer layer shattered. The 2 layers beneath remained intact. One final test still remained. Before the bridge opened, a 2-ton SUV drove across the completed glass deck. No cracks, no dangerous movement. The bridge passed. After that, engineers completed the final static and dynamic load tests before opening to the public. Today, sensors continuously monitor wind conditions, structural behavior, and visitor numbers in real time. No more than 800 people are allowed on the bridge at once, and every visitor wears protective shoe covers to prevent scratches on the glass. When it opened in 2016, the Zhangjiajie glass bridge became both the longest and the highest glass-bottom bridge in the world. Ironically, its first major challenge wasn't engineering, it was popularity. Just 13 days after opening, overwhelming visitor demand forced the bridge to close temporarily while the surrounding infrastructure was upgraded. On foggy mornings, the cliffs vanish, the valley disappears, even the far end of the bridge fades into the clouds. For a few moments, it no longer feels like standing on a bridge. It feels like standing in mid-air. Perhaps that's exactly what Haim Dotan had imagined from the beginning. If you want to keep exploring the world's greatest feats of engineering, join Breakthrough Engineering for the next one.